Swayam Prabha. Digital India. Educated India.
We have discussed rigid rotor and very soon we are going to discuss hydrogen atom. After that we will talk about multi-electron atoms where we will discuss something very strange, enigmatic called spin. And in all these cases one quantity that keeps on coming back at us is angular momentum. So, what we will do in the next 1 or 2 modules is that we are going to discuss quantum mechanical description of this quantity angular momentum. The quantity as such is not very new to us. We are familiar with this kind of a diagram. This is a cartoon that I have downloaded from this website, but in physics we have studied that whenever there is circular motion where the direction of motion is given by the direction of fingers of right hand, angular momentum is a vector that arises perpendicular to the plane of rotation and is along the thumb of this right hand whose fingers are curled to tell us the direction of circular motion. This is of utmost importance because angular momentum is what defines rotational kinetic energy, and when we talk about rigid rotor for example, it is kinetic energy all the way. Remember we had reduced the problem to a one body problem. So, there is no question of potential energy, it is only kinetic energy that we talk about, and that kinetic energy is given by, you might remember, L square by 2I. So, let us see what is the quantum mechanical way of talking about angular momentum, and also what we learn in this module and maybe the next is see we have been talking about this theta and phi part of the wave functions. Phi part I think we understand very well because we actually solved that equation. We did not solve the theta part of the equation, but we proved that Lz has this e to the power im phi, the phi part of the wave function as an eigen function with an eigenvalue of mh cross. So, we said that the z component of the angular momentum of rigid rotor is mh cross, and then we said that the total angular momentum is h cross square multiplied by j into j plus 1. This is something we are going to use in hydrogen atom also. What we have not really explained is why is it that there is an upper limit of the values of m. Why is it that there are 2j plus 1 values of m? In this module or maybe the next we will get to learn that, and initially I did not think I will go that far, but now I am tempted to also talk about ladder operators in angular momentum. Remember ladder operators in rigid rotor. Similarly, we can talk about ladder operators here also, and I am tempted to go a little further and talk a little more about energies and wave functions. Let us see whether we get there, but at least by the end of this discussion we will get to know why there is an upper cap of the values of m, and also we will get to encounter a very important phenomenon in quantum mechanics which involves operators that commute with each other. What is the meaning of commute? I guess you know, but in any case we are going to talk about it. So, here goes. Let us start at the very beginning, and since I have got a feedback from many of our potential students that they would like to have things done from scratch as far as possible, we will start at the very beginning here. We will talk about the classical description, the classical definition of angular momentum. As you know, angular momentum is defined as the cross product of r and p. L is equal to r cross p. What is the meaning of cross product? Magnitude of well, first of all cross product is a vector product, right. Magnitude is given by r, well, magnitude of the two vectors multiplied by each other multiplied by sin theta. And what about direction? Well, we have already talked about direction of the angular momentum vector. Here what we will do is we will work with the components. So, we can write like this, that x, the position we can write as I multiplied by x, well r, sorry, r the position, r is the position vector, right. So, length of the position vector is given by I multiplied by x plus j multiplied by y plus k multiplied by z. Perhaps I do not have to explain to you what I, j, k are, but I still will. I is a unit vector along x axis, j is unit vector along y axis, k is unit vector along z axis, and x, y, z are the magnitudes of the x, y, z coordinates of the point we are talking about in the first place. I hope that is clear. Similarly, P is defined as I into Px plus j into Py plus k into Pz. Please remember these are vector sums, I, j, k are vectors, that is why I have written them in bold and italics, and Px, Py, Pz are the x, y, z components of momentum, linear momentum. X, y, z are x, y, z components of the position, you can say. Okay. So, these are vector sums, please do not forget. Now, when I take a cross product between r and p, what I really have to do is I have to take a cross product between this and this, Ix plus jy plus kz and Ipx plus jpy plus kpz. While doing that, how many terms will I get? Well, 3 into 3, 9 terms. Let us take them in groups. First of all, what you see here is the I cross I, j cross j, k cross k terms, the cross products of the same vectors, same unit vectors. So, Ix cross Ipx gives you I cross I x px. Similarly, jy cross jpy gives you j cross j ypy, kz cross kpz would give you k cross k zpz. Okay. What I cross I, j cross j are, we will come to that shortly, and I am hoping that most of you know anyway. Still, in case you have forgotten or in case you have not come across this, we will do it. What will the next term be? Next term what we can do is we can take in alphabetical order, I cross j, j cross k, k cross I. So, I cross j term what will it be? Ix cross py plus jy, well j cross k will be multiplied by ypz. So, sorry, I will say that again, Ix cross jpy's will be I cross j multiplied by x dot py. Remember, x and py are just magnitudes, the direction is given by the direction of the unit vectors I, j and k. Okay. So, then kz cross kpz would, well sorry, I cross j, j cross k and k cross I. So, kz cross ipx would be k cross I multiplied by zpx. This is what it is. Sorry for the overlap here, it was not like this, but anyway sorry about that. I cross j multiplied by xpy plus j cross k multiplied by ypz plus k cross I multiplied by zpx. So, we have got 6 terms out of the 9 that we promised would be there. What would the last terms be? We can take the reverse order alphabetically. We have taken I cross j, now let us do j cross I. We have taken k cross I, now let us take k cross j, and let us take I cross k. Okay. So, this is what we will get, jy cross Ipx, that gives you j cross I ypx. Then kz cross jpy gives you k cross j multiplied by zpy. Why am I saying j again and again? Kz cross jpy gives us k cross j zpy, and finally Ix cross kpz gives us I cross k xpz, right. These are our 9 terms. Fortunately, not all 9 terms exist. I am sure most of you would know that cross product of same vector is actually 0, sin theta. Remember I said that magnitude contains sin theta, and of course the angle between I and I is 0. So, sin 0 is 0. So, I cross I is equal to j cross j is equal to k cross k is equal to 0. So, these first 3 terms in I cross I, j cross j and k cross k, these are going to become 0 and therefore vanish. We are left with 6 terms, I cross j xpy plus j cross k ypz plus k cross I, sorry about this, plus j cross I ypx plus k cross j zpy plus I cross k xpz. Okay. Maybe I will just correct this for you, otherwise it is difficult to see. Okay, that is much better. So, I have I cross j xpy plus j cross k ypz plus k cross y zpx plus j cross I ypx plus k cross j zpy plus I cross k xpz, 6 terms. Now, we need to know what is I cross j, what is j cross k, so on and so forth, and that is also very well known. These are unit vectors, remember. So, unit vector means magnitude is 1 and I, j, k are perpendicular to each other. So, when you take cross products of say I and j, you get the third one, I cross j is k, j cross k is I, k cross I is j. When you take them in the correct cyclic order, you take them in reverse cyclic order, instead of I cross j you write j cross I, it just becomes minus k, okay. X y z it becomes minus z, something like that. K cross j is minus I and I cross k is minus j, okay. These are very standard things that one learns while studying the chapter on vector in higher secondary mathematics. Good. So, let us start substituting. The first term we have is I cross j, instead of I cross j we will write k. Second one is j cross k. What is j cross k? J cross k is obviously I. It is very simple, I mean you just write the third one. If it is in correct cyclic order you write plus sign, if it is in reverse cyclic order you write minus sign. So, j cross k is going to be I, k cross I correct cyclic order is going to be j. Now, j cross I is reverse cyclic order, right, in alphabet I comes before j. So, you are going to get minus k. K cross j similarly is minus I and I cross k is similarly minus j. So, now what we can do is we can collect the terms in I and j and k and we can get instead of 6 terms we can get 3 terms. So, if I collect the terms in I, what do I get? I multiplied by ypz minus zpy, is not it? J multiplied by zpx minus xpz and k multiplied by xpy minus ypx, right. So, I into ypz minus zpy, j into zpx minus xpz and k into xpy minus ypx. Okay. What I really need you to do is please make sure you have a pen and paper in your hand when you attend these modules. You should keep writing, that way you understand better. If you just look at the screen you may get it, may not get it. Of course, the advantages is that you can pause me and you can write, do it, no problem. But please write when you are hearing, otherwise it is then it will register better. The more senses we use while studying, better we grasp it, okay. That is a very well known phenomenon. Okay. So, remember this, I multiplied by ypz minus zpy plus j multiplied by zpx minus xpz plus k multiplied by xpy minus ypx, alright. So, now see what is this, that right hand side is an expression for angular momentum. So, obviously whatever is multiplying I is the x component of angular momentum, whatever is multiplying j is y component of angular momentum, whatever is multiplying k is z component of angular momentum. So, we can write Lx is equal to ypz minus zpy, very nice, right, ypz minus zpy, and what is that equal to? Lx. So, you can think like this, if you think of 3 random variables, I cannot use ijk and I cannot use xyz. So, maybe we will say pqr, is pqr, no, p is also there. So, we cannot use let me say 1, 2, 3, that is better. So, you can think like this, when you talk about the components, L1 is equal to I into 2 P3 minus 3 P2 plus J into 3 P1, well sorry, Ly. So, that is your x component, right. L1 is equal to, well that holds for everything actually, L1 equal to 2 multiplied by P3 minus 3 P2. Okay. This is a general way of writing your x, y and z components of angular momentum. Okay. So, let us write that. This is what we have. One way in which we can express very nicely, and we are going to come across this tool in some other context also, is determinants. Okay. I hope we all know what determinants are. If not, please brush up. It is just a way of writing sums like this. In a determinant, what you have is, if you have something like, I will just write once. Okay. In case somebody needs to know how a determinant is written, I will just write it once. This is a determinant, you write like this, say A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3, A 3 1, A 3 2, A 3 3. This can be anything, we will just see an example of a determinant that is useful for us. Okay. But this is what a determinant is, and what it means essentially is, you take A11 multiply by this A22 into A33 minus A32 into A33, A32 into A23. So, this determinant will be A11 into A22 into A33 minus A32 into A23. Then next term is in A12, but A12, the second term has a minus sign. So, you can write A minus A12 multiplied by again A21 A3. So, what you do is, you are leaving out this column and this row, whatever is left in that block you take cross product and subtract the other diagonal product. So, A12 is in the first row and second column. So, leave out those, multiplied by, you can write A21 multiplied by A33 minus A31 A23. Okay. Or if we want to write plus, then all that will happen is that this will become plus and this will become minus. Then again plus A13, A13 is first row and third column. So, leave those out, it will be A21 into A32 minus A31 into A22, A21 A32 minus A31 A22. Okay. So, this is how determinant is written, and if you now compare this what I have written here by hand with what I have here, you can correlate, right. A11 in this case is I, A22 is Y, A33 is PZ, A32 is Z, A23 is PY, A12 is J, A21 is ZPX, A33 sorry A21 is Z, A33 is PX. Sorry, this is there is a minus sign here. So, this has to come here. So, A21 is actually X and A33. So, this way you can just correlate with these, and we will just write it in the determinant form. Before that, let me erase this. Now, let us show you the determinant here. This is what it is. So, ijk xyz px py pz, very nice, right. The way we have written it is that the first row is just the unit vectors along x, y and z. The second row is the xyz coordinates, right, position. Third row is px, py and pz, the components of angular momentum along x, y and z. So, very nice systematic way. If you go from left to right, you go from x direction to y direction to z direction. If you go from top to bottom, you go from the unit vector to position to momentum. It is very nice systematic way of writing it, and this is how it expands. Okay. ypz minus zpy j into zpx minus xpz, remember j had a minus sign, so that has gone in, plus k into xpy minus ypx. Okay. This is what the determinant is. Now, we know the x, y and z components already, these are the x, y and z components. The other quantity that is very important is L square, square of angular momentum, and you will appreciate it even more when we go into quantum mechanical description. Okay. That is given by Lx square plus Ly square plus Lz square. I hope I will not work this out explicitly because I have worked out the other one, you can do it yourself. But remember, when you try to do L dot L, that is a dot product first of all. So, it will be a scalar product, no direction. But then you have to take I into Lx plus I is j into Ly plus k into Lz, take dot product of that with itself. While doing that, you have to remember that I dot I is equal to j dot j is equal to k dot k is equal to 1, and I dot j is equal to j dot k is equal to k dot I is equal to the same thing written in the other direction is equal to 0, because dot product has cos theta in the expression. So, if angle between the two vectors is 90 degrees, then of course you are going to get 0. Okay. So, that is how we get Lx square plus Ly square plus Lz square. It is important to understand that this is a scalar quantity, not a vector quantity, and Lx, Ly, Lz are the components of angular momentum, which itself is a vector quantity. So, this is the classical description of angular momentum. Now, let us just build the quantum mechanical description, and then we will end this module. We will go to the next module for the next part. So, the quantum mechanical description is, as you know, we start from the classical definition, and what we do is for every variable, every observable that is there, we replace it by the corresponding operator, right. So, if you want to write this matrix, what do we have to do? We have to replace x by the position operator x, which is just multiplying it by itself. You have to replace px by the momentum operator px hat. Okay. So, these are the two rows in which this matrix is going to in which this determinant is going to look different, but mean the same when we try and build a quantum mechanical description. While doing that, x hat is very simple. Remember, pq hat, where q can be x or y or z, is h cross by I del del q, or you can write minus I h cross del del q. In the later part we have actually used that minus I h cross, it means the same, it is no big deal, do not forget. The way I remember it is that where if I is in the denominator, then it is positive, if I is in the numerator, then it is negative. H cross always is in the numerator, of course. Okay. Now, with that, let us try to write a similar determinant for the L hat operator, the angular momentum operator. What will it be? It will be something like this. First row remains the same, ijk, second row also remains the same. In the third row you are going to have h cross by I del del x, h cross by I del del y, h cross by I del del z. So, you might as well take the constant h cross by I outside the determinant, because the determinant multiplied by a constant is what you get, and then the x component very similar to what you have there, instead of pz you write pz hat, that is all. Instead of I have made a mistake here, sorry about that. it is not z y hat, it is z p y hat. Of course, it is obvious, but it is a typo. Let us see if I have repeated the typo later. I have not. Ly is equal to Ly hat is equal to z p x hat minus x p z hat. Please do not forget that this is actually p y hat, this is a typo here. Maybe I will just write it with my pen. So, this one I will cut and I will write p y hat for you. Good. Lz hat. Lz hat is x p y hat minus y p x hat. Okay. These are the operators for Lx and Ly and Lz components, and these operators are extremely useful. You keep on using them in many situations later on. So, Lx you can write like this, instead of pz hat you write this del z, and this is similar. Now, what about L square operator? L square operator, for that you have to simply substitute this by Lx square, Ly square, Lz square, okay, and that will come from these Lx operators. So, I am not working it out explicitly, we will do it whenever required, but please remember that we have to build an operator for Lx square, L square also. In fact, that is the most useful operator. I am not doing it because we are not going to use the Cartesian form, we are going to use the spherical polar coordinate form. Remember, your rigid rotor problem or any problem where rotation is involved, angular momentum means rotation, some sort of rotation would be there, notionally yes, even though for hydrogen atom we say that we cannot talk about rotation, but still angular momentum is there, same for spin, but we will cross those bridges when we come to them. But what I am saying is this L square operator is actually of utmost importance, okay, that is what we work with, and we always use this spherical polar coordinate form, which you do not have to remember, we will give it to you. But since we are talking about spherical polar coordinate form, it makes perfect sense to show you what these Lx hat, Ly hat and Lz hat operators are for in these spherical polar coordinates. Okay. This minus IH cross multiplied by minus sin phi del theta minus cot theta cos phi del phi, this is Lx hat operator. Sometimes I make mistakes in writing these expressions, so please cross check with the book. This part you can study from Pillar's book, but I have followed Macquarie and Simon physical chemistry, Macquarie quantum chemistry book, or Prasad, or any book that you are comfortable with. Okay. But please double check and make sure that whatever is there is correct. Okay. It should not be that I make a mistake while typing here and then I do not notice it and you learn the wrong expression, that should not be the case. Okay. This is Lx hat. Next we have Ly hat, very similar, instead of sine we have cos, instead of cos we have sine. Lz hat fortunately is very simple, IH cross del phi. Why is Lz hat so simple? Because remember what is phi, we have talked about this while talking about rigid rotor. Changing phi essentially means circular motion in the xy plane. So, the associated angular momentum has to be in z direction. So, that is Lz hat, and it makes perfect sense. You can correlate it, you can correlate say Lz hat, the angular momentum operator in z direction with the linear momentum operator also, they are very similar, is not it? This is h cross by I or minus I h cross del q. You can even write this as h cross by I del q if you write q equal to phi, very similar. What linear momentum is in a linear motion, angular momentum is in circular motion. It is very important to get these correlations right. And sometimes students ask this question, how do I know? How do I know which is x axis, which is y axis, which is z axis? And the honest answer to that is that we do not. We define one direction as z. If we have an external perturbation, like if we apply an external field, electric field or magnetic field, then of course we define that to be z axis. Why? Because then we have to deal with an easier operator. Okay? So, it is of course in our hands, but you will see that we will always work with the z direction because it is easier to handle. Okay? Maybe we will stop this module here and continue from here in the next module.